Have you ever had to determine the appropriate traffic control for an intersection, select a design alternative for a roadway, or choose one safety countermeasure over another? How did you know which one to select? Crash modification factors, or CMFs, can help with your decision. CMFs are numerical values that represent the expected safety effect of changing the geometric or operational conditions of the roadway. You can use CMFs to quantify the expected change in crashes from implementing a countermeasure or to compare the effect of alternative designs. This video uses the term countermeasure to describe a general change in the geometric or operational conditions implemented to achieve a specific performance outcome of the roadway. CMFs can help you make decisions throughout the project development process and allow you to consider the safety effects of a countermeasure alongside other factors such as operational performance and environmental impacts. Applying CMFs is straightforward. You simply multiply the CMF by an estimate of crashes without the countermeasure to estimate the crashes with the countermeasure. This video describes the process of applying CMFs to estimate countermeasure effectiveness, assuming you're familiar with selecting appropriate CMFs and estimating the safety performance of the base condition. You can refer to the resources webpage listed at the end of this video for further information on selecting CMFs and estimating the safety performance of the base condition. In this video, you will learn how to define the base condition, apply the CMF to estimate the safety performance for the condition with the countermeasure of interest, and compute and interpret confidence intervals. Let's start with the basics by focusing on the application of a single CMF. If you're estimating the safety effect of multiple countermeasures requiring the use of multiple CMFs, then you should refer to the training video on the resource page on how to estimate combined countermeasure effects. The first step to applying CMFs is defining the base condition. The base condition is typically the no-build scenario or the condition without the countermeasure. The base condition is important because it influences the selection of an appropriate CMF and the approach to estimate the safety performance of the base condition. For roadway segments, you typically define the base condition by the area type, such as rural, urban, or suburban, number of lanes, and median type. For example, you could define a roadway segment as a rural, 2-lane undivided road or an urban 4-lane divided road. For intersections or junctions, you typically define the base condition by the area type, traffic control, number of approaches, and number of lanes on the major and minor roads. For example, you could define an intersection as a rural, 4-legged, 2-way, stop-controlled intersection between 2-lane roads. Now that you've defined the base condition, it's necessary to estimate the number of crashes for the base condition. This represents the long-term average crashes without treatment. Because the remainder of your calculations hinge on this estimate, it's important to estimate this value as reliably as possible. Before you choose an approach to estimate the safety performance of the base condition, you should consider the level of rigor and scope of the project. Also consider the strengths and limitations of the approaches. The reliability of the analysis approach impacts the reliability of the results. There are 3 approaches for estimating the number of crashes for the base condition in order of increasing reliability: observed crash frequency, predicted crash frequency, expected crash frequency. Once you have gone through the steps to select an appropriate CMF and estimate the safety performance of the base condition, you are ready to apply the CMF. To estimate the crashes for the condition with the countermeasure, multiply the estimated crashes for the base condition by the CMF, as shown in this equation. Let's assume the long-term average crash frequency for a roadway segment is 5.0 crashes per year under base conditions. Also, let's assume the CMF for the countermeasure is 0.8, and this applies to total crashes. The estimated crash frequency with the countermeasure is shown in this equation. You should only apply CMFs within the context they were developed. For example, this table presents CMFs for installing a traffic signal at a stop-controlled intersection. The context of the roadway is a rural 3- or 4-legged minor road stop-controlled intersection within the specified range of traffic volumes. If your base condition differs from these conditions, you should consider using a CMF with a base condition that better matches the conditions of interest. In this example, if your intersection is in an urban setting, then this CMF may not be the most appropriate. The CMFs in this table apply to specific crash types and severities. The important takeaway is that you should only apply CMFs to the applicable crash types and severities. For example, you can use the CMF for right-angle crashes to estimate the change in right-angle crashes. However, it would not be appropriate to use the CMF for all crashes to estimate the change in a specific crash type or crash severity. The CMFs for a given countermeasure may indicate an expected reduction in certain crashes, indicated by CMFs less than 1, and an expected increase in other crashes, indicated by CMFs greater than 1. This table, from the Highway Safety Manual, indicates that the conversion of a rural, stop-controlled intersection to a traffic signal is expected to reduce angle and turning crashes while increasing rear-end crashes. The net effect should be a reduction in overall crash frequency and severity, but this depends on the estimated number of angle, turning, and rear-end crashes for base conditions. If the net effect is an increase in crashes, particularly fatal and injury crashes, then it may be appropriate to consider an alternative countermeasure. Imagine you're considering the conversion of two different minor road stop-controlled intersections to signalized intersections. You've estimated the crashes by crash type for the two base conditions, as shown in this table. You then multiply the estimated crashes for the base condition by the CMF for the respective crash type to estimate the crashes with a traffic signal. The net effect is the difference between the sum of estimated crashes without the countermeasure and the sum of estimated crashes with the countermeasure. For scenario 1, there are 9.9 crashes without the countermeasure and 8.2 crashes with the countermeasure. The net change is a reduction of 1.7 crashes per year. For scenario 2, there are 9.9 crashes without the countermeasure and 11.2 crashes with the countermeasure. The net change is an increase of 1.3 crashes per year. This example illustrates the importance of considering the change in crashes by type or severity. This provides you with a more comprehensive understanding of the net benefits. If you are considering these benefits in a benefit-cost analysis, you could first convert the change in crashes to monetary values by crash type or severity before aggregating to a net benefit. Now you have an estimate of the expected change in crashes, but this doesn't tell the whole story. Computing the confidence interval can help you make even more informed decisions. Specifically, the confidence interval helps you to understand the reliability of the CMF and statistical significance of the change in crashes. As another way to look at this, the CMF represents an average value based on several data points. The confidence interval tells you that the true value of the CMF is likely to fall within some range at the given level of confidence. You can be more certain in the value of the CMF as the width of the confidence interval decreases. You can calculate the confidence interval using this equation and the values from the table. The left-hand side of the equation represents the confidence interval for the given level of confidence. On the right-hand side, the CMF is the crash modification factor for the countermeasure of interest. MSE is the multiple of the standard error, as shown in the table, and SE is the standard error of the CMF. For example, assume a CMF for a countermeasure you selected is 0.75 with a standard error of 0.17. Let's also assume you would like to calculate the 95% confidence interval for this CMF. You first need to determine the appropriate multiple of standard error from the table, given the desired level of confidence. For a 95% confidence interval, the factor is 2. Now you can compute the 95% confidence interval as shown in the equation. This gives a confidence interval of 0.41 to 1.09. If the confidence interval does not include 1.0, you can conclude that the CMF is statistically significant at the given confidence level. If the confidence interval includes the value 1.0, as is the case in this example, then you can conclude that the CMF is not statistically different from 1.0 at the given confidence level. You should be cautious when applying CMFs with a confidence interval that includes 1.0, because this indicates the countermeasure may result in a reduction, no change, or an increase in crashes. Had you used only the point estimate of the CMF, you would have expected a 25% reduction in crashes from implementing the countermeasure. If you compute the confidence interval, you can understand the potential range of effects. For example, let's assume you're using these results in an economic analysis. To be conservative, you decide to use the upper end of the 95% confidence interval to represent the safety benefit for the analysis. In this example, the upper limit of the 95% confidence interval is 1.09, which indicates a potential 9% increase in crashes over the base condition. This video demonstrated the application of CMFs to estimate countermeasure effectiveness. Refer to this resource page for additional guidance, examples, and courses on applying CMFs. At the Federal Highway Administration, safety is our top priority. For more information, visit us online at safety.fhwa.dot.gov.